So I have solved it this way. I have solved it this way. So I first have found out you don't need necessarily to do this way, but I think it's the easiest way to understand it because we have two different forces what we are using there. So I first find out what is the maximum force what we can use here. So it's not sliding, and we have found that it's 11.76 newtons. The bigger force is than this one, it starts sliding. And our A part was the force is 6 newton. So if the force was 6 newton, we know it's not sliding. So force is 6 newton. Then we can find out, we can go these formulas back here and we can find out everything what we need here. If F is 6 newton, if F is 6 newton, friction force must be 2 newton. 6 newton is 3 times 2 newton. So we have found that friction force is now 2 newton in this case. And these formulas we can use all the time. So F plus F nu must be mass times acceleration. And we get here acceleration is 4 and the angular acceleration is 20. And to the B part. And B part we know it's sliding. Because in the B we are using force 16 newton. And now it's easier for us because in the A part, this friction force here, this 2 newtons, it's not the maximum friction force and you static friction. And remember one thing, you don't have any formula for the static friction. You have only formula for the maximum static friction. But now in the B case, it's easier because you know it's sliding. You know it's sliding, so you know the friction what we have now is the kinetic friction. And kinetic friction you can always find out. Kinetic friction is always the coefficient of friction, kinetic friction times normal force, and in our case normal force is mg. So the friction force now we found is easy to calculate the value of this. So we know the 16 newtons is F mu k. We can now calculate it because this is the kinetic friction, and acceleration, we can use this formula here. And now notice, these formulas would be found at the beginning here. They are separated formulas. This is formula for the translation, and this is formula for rotation, but they don't have any, this is formula for rotation, because now we don't anymore have this connection at all at the B part. But we calculate them separately. The translation part, Newton's law goes like this, so the acceleration must be like this. And for the rotational part, we have still this formula. We have still this formula going on there. And now we know the friction force, 2.94. So for here we can find out. And in this kind of case, the B case, when it's sliding, there's no more this connection. So the angular acceleration is not anymore same than acceleration divided by radius. And to B part, you must do it separately. First, think what happened to the translation. You can find this acceleration, and then you think what happens in the rotation, and you use this formula here. Okay, so I think we.
Sorry, I have a question. Can you tell more specific why in the first rolling problem we have the static friction at the opposite direction with the force that make the object move, and in this case we have it in the same direction?
I try to show you again. This is this. I put it on. Let's try if I get my camera here. Okay, let's do it this way. So this is this wheel now. I hope you can see this now. And now if I push here, now it's rolling. Now it's rolling. There is no sliding there, as you see. And now if I put more force here, it goes like this now. As you see, it's flipping there now. The more force from here start slipping like this. And what I need to prevent this kind of flipping, as you see, I'll put it here. Wait a minute, my camera's now you can try to see it. It's do this kind of movement if the force is too big. So it's flipping this way. And there, if I have enough static force here, so this static force prevents the slipping. That's why. You can test it for yourself. It's easy to find out, but that's why. This static friction here, it's preventing this. If you have, for example, we take today example of cars, and when a car wheel rotating this way, only force which prevented to the sliding there. So it's very big rotation and not any translation there. So friction force must be in these times, in this direction. This force here makes a rotation, but this now is preventing the sliding. And it's very hard sometimes to thinking depends where this force is. For example, if this force is in the middle, let's put this example like here. Same situation now. If this force is starting from the middle, if I now do pulling with this kind of force, and what I need if it's rolling here, this is the direction of rotation. And if this is the direction of the rotation, now if I pull it from here, so to get this rotation here, we need a force there. And this force can't do anything about rotation because it has no torque on this object. So in this case, now the friction force must be this direction. But this case here, we can easily find out what. This is the easiest to think if you think you push this very fast here, start to make it rotation. So it starts really sliding in other direction. So now you need, in this case, you need friction force from here, and in this case, you need a friction force here. And as we do this yo-yo example here, now the friction force, you have found the rotation of this because now if we go under there, this was our one homework. We've used force here, and now we need the rotation also. You know, this goes this way. Sorry, my paper is here. This goes this way. We can see that if we have enough friction there. So in this case, where the friction is, we need to rotation this way. So we need to have now friction this way. It's depending. Sometimes you must think in this. We go back to this example today when we think about a moving car. I think it's easier to understand this, what happens there. Okay, but now I think we do some rotational problems together here, and let's try to really do this together. So let's do the thinking part together, and I try to go a little slow there. So we have a problem number 3, and let's put it a little bigger if you can, so you can read it here. This is also in the Moodle. This is on the same problems and number 3 here, and we have this kind of situation. The billiard ball is initially sliding without rolling at linear speed on the horizontal surface. So we know the coefficient of friction between ball and the surface, and we're trying to find the speed of the ball when it begins to roll without sliding, and so also the elapsed time. Has any one of you any time been to bowling? Are there bowlers in this group? And the bowling ball, for example, acts kind of like this. When you throw the ball, when you throw the bowling ball, let's put this situation. What happens here? Uh, when you throw to the bowling ball at the beginning, it don't. Of course, you can make little rotation at when you're throwing it. But if you throw the bowling ball without giving any spin of there, so it's not rotating at all at the beginning. But then it starts to go there, and after some time, it's rolling. It's not anymore. At the beginning, it only has the translation, not rolling. It starts rolling, but it's sliding a little. And at the end, we have a clear rolling case. So it's rolling without sliding at the end. And let's try to find out this, what happens there in this billiard ball same way. So we have it starts from here. We have just draw it, and we have a linear speed of 4 meters seconds. So we have an initial velocity here, and we have initial velocity 4 meters per second. But it's not due to rotation. So we have initial angular velocity is 0. This is our situation at the beginning. And this is at the end. It's asked for us what is the velocity when it stops sliding. So we are looking for now this velocity when it has stopped sliding. And in this case, when it's not sliding anymore, it has some angular velocity. And now if this is really, here it starts rolling, it starts rolling at this point. So now we know the connection between this angular velocity and velocity. At the end, when it starts rolling, we know that V must be R times omega. Now we have this connection there. No more sliding. But the sliding ends here. It starts rolling without sliding. So this is our situation. And let's try to figure out how we can solve. So first we're trying to find the method what we are using. And I think let's use the Newton's laws on this case. So let's start with this translation part. Let's check only the translation from here to here. So only the translation part, and the Newton's laws told force is mass times acceleration. And now let's think what kind of forces we have there. So it starts with the sliding. It don't rotating at all at the beginning. So far when sliding, when we are not on here at the end, we have a friction force there. And friction force here try to prevent this slide, and it's a kinetic friction. We have kinetic friction here, if we think this translation part. And this kinetic friction is so far when we are at this point, and at this point it's ended. After that, when the sliding ended, our friction force is now static friction. But from here to here, so far, due to also the little sliding there, it kind of sliver there, so we have a kinetic friction force. So in the translation part, from here to here, we know that net force must be mass times acceleration. So net force must be, in our case, it must be minus F mu K, because the direction is this way, this a little smaller, and this must be mass times acceleration. So far, so good. Okay. And this F mu K, what we have here, so we really have a formula for the kinetic friction. So the kinetic friction is a coefficient of kinetic friction multiplied with normal force. And normal force in this case, normal force here, and mg here. The normal force must be mg. So the minus F mu K is minus mu K times normal force, but normal force we found out here is mg. So we have here like this, and here we can find out the acceleration. Because I think we need the acceleration, we are trying to find out the velocities and the time, so it's sometimes this must be some kind of kinetic problem. So the acceleration here is not depending on the mass at all, it's minus mu K times G. So we have this kind of acceleration, so it's slowing down, of course. It's not anymore this 4 meters per second at the end, it's a little more less than, because it's slowing down there. So, and the acceleration with slowing down, negative acceleration, deceleration is minus mu K times G. Okay, and when we talk about velocities here, let's try to find out, can we find any formula for this velocity what we are looking for? And in the translation part here, so we know delta V acceleration is delta V per T, so V must be, V at the end must be V0 plus acceleration we know. We know because according to the acceleration and change of the velocity divided by time, so the final velocity must be initial velocity plus acceleration times time. So, because we are looking for this V, so we have some equation for the V. We have, so that V is V0, what we know there, 4 meters per second, plus acceleration is minus, let's put it here, middle to minus MUK times G times T. And what we have found? We have found equation where we have both unknowns what we need. We were asked what was the velocity here, so it's there, and we were asked also the time it takes. So we have a time here. So now we have found out one equation for us, but we have two unknowns. So let's try to find out the second equation, what we are going to use. And let's go to rotation part. Let's study what happened in the rotation. I think we can get there out other connection between the velocities and time. For the rotation part here, so let's take again Newton's second law there. Newton's second law for rotation was the net torque. The net torque must be moment of inertia times angular acceleration, like this. And let's try this little out what we get here. We have only one force which give a torque. There is a friction force. It's a kinetic friction force there. This one give a torque, so it starts rotating. So this is F mu K. Note now it's a positive because we have a positive direction there. F mu K times the radius of this ball. The moment arm is radius. Here is the radius of this ball, like this. And on the other direction, what we have a moment of inertia of this ball. And the moment of inertia of the ball, we can find from the tables. You use in your homework these values. It's the moment of inertia of the ball is 2 per 5 times mass times radius power 2. Sorry, it goes there. So here is the moment of inertia of our ball. So moment of inertia 2 per 5 times m r power 2 here times angular acceleration. Okay. This we have found of the rotation, Newton's second law for rotation now. And then let's go to this kinetic, what we need to cut out there. So this angular acceleration, what we have there, must be same way the kinetic part here, kinetic of rotation. The angular acceleration must be the change of the angular velocity divided by time. So we can get same way here. The angular velocity at the end must be angular velocity at the beginning plus angular acceleration time. And this was 0. It was 0 at the beginning, so we have a simplified little, we have here like this. But now, we have found from the rotation this part here, angular acceleration all the time same there. We know we can a little simplify this if you like this F mu K, because we know F mu K. Let's start this first. F mu K must be mu K times mg, this part here, times r here, and we have the other side, we have 2 per 5 times mass times. So we can a little simplify this one because, as you see, we can take m away from there. We can divide it with m, both sides of this one. We can take the masses away, and also one radius if we like. So we have a little simplified this one. So we get here now to what we have left here. We have mu k times g is 2 per 5 times r times angular acceleration. So I'm working with this formula. I'm working this formula, a little simplify this. I put the knowledge of what is the friction, kinetic friction force, and take the masses after that away and one radius, because I said there's one radius and there's radius power 2. So I get this kind of situation. So let's check what we can do next here. And let's go this part, what we found here. And we go to the end here, because this is now what we have found out. This is the final, this is exactly this angular velocity, what we have here. This is angular acceleration, what we have there, and this is the time what it takes there. But we remember something. At the end, we have already this one, this knowledge we have at the end. We know at when it starts sliding. And what symbols we have here? This angular velocity here is the angular velocity at the end. But we know at the angular velocity at the end must be v divided by r. So let's work with this formula. Angular velocity at the end is this one. And this must be same than v per r. V per r is angular acceleration times t. I think this could be an easier way, but trying to think all the time what we are doing here. So now we have angular acceleration. We don't need it here. We need to v. We need it here. So let's take this way. So angular acceleration here from here is v velocity at the end divided by radius and time from here to angular acceleration. I simply divide it by time. And now we have this formula, what we are thinking. The mu kg is 2 per 5 times r times angular acceleration. And we have just found out how we can tell angular acceleration in the help of the velocity and time and the radius. So let's try to put this angular acceleration here. So mu k times g is 2 per 5 times r times angular acceleration, which is v divided r by g. And we notice that we can get r out there. So we have here this is not the only way to do the solution, but I think I have find out what I'm looking for. And what we were looking for, we were looking for another formula. Other formula which contains velocity, and unknown g. And now these two formulas together. We can continue. I take one empty paper somewhere. Wait a minute. From here. So what we can find out here, V is V0 minus mu K times G times T was the first formula what we have there. We get this from the translation part, and we get now the mu K times G is 2 per 5 times V divided by T. And the problem was what is velocity at the end and how much time it has taken. So we get two formulas now and two unknowns there. So we can pick up our way to figure it out. One way is if you look in these two formulas, but now not simply mathematics. Do whatever you like. But I see here this is the mu kg and here is mu kg here. So if we try this, if we put this mu kg on this first equation, let's try to finish this. V is V0 minus mu kg, but mu kg is 2 per 5 times V per T, 2 per 5 times V per T times T. I think this is the simplest way because now we have eliminated the T here, so we can find out 7 per 5 V 5 per 5, 7 per 5 V is V0. So the V must be 5 per 7 V0. And V0 we have, if we take numeric value here, 5 per 7 times 4 meter per second. And let's hope that we can manage to do right conclusions there. So 20 divided by 7 is 2.86 meter per second. 2.86 meter per second. And there's answer for the velocity. The whole calculations are here. Answer for the velocity, and it's also asked for us the time. So we have any place to here find out. For example, here you can find the time. You now know velocity, initial velocity. You know mu k is 0.2 and g is 9.81. So you can get the time out there. I put this solution also to the Moodle after these lessons or during this day. So if you don't manage to follow all the time, I try to make it also a little cleaner what we have done here. And let's go to our last problem about rolling. And I ask you, is there a bowlers inside here? Now I ask if there are billiard players. I try to find out this last problem I plan to do with you. Wait a minute. I have so many papers here. Here, very simple problem for billiard players. And for all of us, we also want to, oh, wait a minute. No, it's something that goes very badly. No, now it's focused rather good. Okay. Question is following. Where is the place you hit the billiard ball so it starts rolling without sliding? The place of where you hit the ball. And now notice we have no friction at the surface. Let's try to figure it out. What is the point you need that it starts really rolling there? So free body diagram here. Oh, wait a minute, this don't work at all. So here's a ball. Here is a surface here, and to get it rolling first, and there's no friction, so we need to go this way. So one thing we already know, if the center of mass of the ball is here, and we needed to make a direction of rotation this way, so we need the place of the force we use must be over this center of mass, just like in the picture. So the force is somewhere there. Force is somewhere there. And we have the radius of this ball is r. And let's find out this h, what we have here. So mg we have there, we have a normal force there, but we don't need a normal force because it's told us we have no friction at all there. At all, any friction. Okay. And idea is that it's not sliding there. So what we have there, we have the acceleration it get here. It must have a connection of the angular acceleration here. So again, without sliding these kind of things, we know that the connection between this acceleration what ball gets and angular acceleration must be here. That we know. Then we know also we have a translation and rotation. And if we think translation part here, so one more time, Newton's second for translation, force is mass times acceleration, and our force is really, we have only one force here on the direction of the movement there. So it is simply force is mass times acceleration, nothing else. And for rotation, if you think for rotation, you have a formula, Newton's second for rotation, and it goes net torque is moment of inertia times angular acceleration. And let's put these formula values. So now we have only one force that gives the torque here is the force. And we need the moment arm of there. So where is the moment arm of there? The direction line of force is here and the axis is here. So here is the moment arm. And our values what we have here, it must be H minus R. This here is, if we use these figures here, it must be H minus R. Okay, so we can get this side of formula here. The torque is force times the moment arm was H minus R. H minus R, like this. This is our net torque. And now the moment of inertia, and same way as we do on the earlier case, we have found out we know the moment of inertia of the ball is 2 per 5. 2 per 5 times mass times radius powered 2. And our angular acceleration here, because there is no sliding case now here, we have this connection there. So the angular acceleration must be acceleration divided by radius, like this. And if we put these together, we have force is mass times acceleration. Let's try to find out. And again, we can a little simplify this one. We can simplify here. We can take 1r wave here, and we can take here. And now one possibility to get this one out, as you see here, I like to do this way because here we have mass times acceleration. Mass times acceleration we have here, and we have always here knowledge that mass times acceleration is the force. So we can put instead of mass times acceleration here the force. So it's 2 per 5 times force times R. So I simply take here, there is mass times acceleration, here is mass times acceleration. So I put these two formulas together like this, and then let's open these brackets and let's find we'll try to find what we find out there. So F times H minus F times R is, or wait a minute, I'm going to sleep now. Why to do this way? Because let's take F away. We have both sides of the equation. We have F. So it doesn't matter what the force is. Only matters the place where it hit. And the place where it hit must be here. H minus R is 2 per 5 R. and we are looking for this place here, so it must be H is 5 per 5 plus 2 per 5, 7 per 5 R. This is very easy to test, for example. If you have some heavy ball and you have very slippery surface, you can easily test what happens if you hit there, and billiard players knows, of course, if you want to do the spin to the ball. If you want to make a spin to the ball, you hit here or you hit here. So it's now we have some spin on the ball. Okay, I think this was the last case what we do together about rolling problems. Or I just get one idea here. Let's do one more. We have, or at least let's make your homework for you. Yes, let's make homework for you because we get the. So as you see, I put on the table the yo-yo again, and now my question is I try to take some room there and turn the camera a little. This is very, wait a minute, can I turn it here? Oh, it's upside down now for you. Let's go this way. Hello, hello, here. I think you don't want to see me, you want to see here something. Let's try to find out. This is like to be in TV show. Okay. You can see now. Okay. As you see, I'm not a master of this one, but let's make our problem here. I'm going to ask you what will be the acceleration of this yo-yo when I drop it like this. Acceleration of this yo-yo. And if you want a very easy version of this question, I ask acceleration this way. And if you want the easy B part of this problem, acceleration now, if I don't use the string here, this is of course 9.8 meter, but original problem was this one. When I drop this yo-yo and holding to this rope, acceleration of this yo-yo. And trying to find a paper for us somewhere. Okay, are we ready? Are we ready for our problem? Let's put it this way. Okay. Like this. And of course, what we need first, we need some kind of free body picture of this happening. What we have here, this is a yo-yo here, and our problem was the acceleration of this yo-yo. Acceleration of yo-yo. And let's draw the picture here. This is our yo-yo. This is this little stem inside there. And string comes here like this, and question was what is the acceleration when we drop it here. So I don't have a scale here. I can, of course, I can measure this yo-yo, but let's do the case that any kind of or any size of yo-yo. Let's do it without any numeric values. We can measure this afterwards and testing if we were right. But let's take only that the mass of this yo-yo is m, and we need two radius there. Of course, we need two radius there. So let's say the inner outer radius here, I mark it r, and inner radius, this stem what we have inside here, let's mark it little r. So we have two radius there, outer radius, and this inner stem what we have, the radius of that. And now we're assuming something. We're assuming that this thin rope here, this string what we have is very thin. So let's, in the real case, the radius change all the time. This inner radius change all the time because we have more string over there or less string in there. But let's keep it, this string is very thin. Let's simplify this. We can later think real situation if the radius turning all the time, it's changing all the time because it's really little changing. But let's take the radius of the stem, and this string is very thin, so this is about constant, this r. It makes it a little easier for us. Also, let's assume that also this yo-yo is a disk. It's a really, we're assuming yo-yo is disk, homogenic disk, and this was what we have assuming, and we are assuming that this string is very thin. With these two assumings, what was the acceleration of the yo-yo? And let's take a couple of things together. Oh, what the hell? Let's calculate this together. So Easter is coming, and I don't know if you like the homework for the Easter. So let's try to. We have enough time. We have one subject left here. So I think we have enough time to take this at the end together. But let's try to do it together now. I'll give you some time to thinking about this problem, and then one thing I know, you don't need any thinking because we have do so many of these kind of problems. So I think where you're starting this one, it's our subject of this today and last week. I think this is a good place to starting to solving this problem. The net force must be mass times acceleration, and net torque must be moment of inertia times angular acceleration. And as you see, the acceleration, what we have there, what we are looking for, and this string is not flipping at all. So we have certain connection there. We know something about the acceleration and something about angular acceleration. How they're depending about each other. So and I hope you have already drawn some kind of free body diagrams there. You have found the forces, what we are having there. There are not so many forces. We have G here, and we have a tension of the string here. These two forces we have. So the second law of dynamics on the straight line motion, the direction is there, so it must be mg minus t must be mass times acceleration. This was a direction of acceleration. The direction of rotation and direction of angular acceleration must be there. So net torque, only one force gives torque here, is T. And the moment arm there, notice the moment arm there must be little r. The action line of the tension axis there, so T times R. This must be the net torque here, and we assume that the yo-yo was the disk, so the moment of inertia of the disk, we know it's a half time mass, and this must be of course the radius of the outer radius of the yo-yo. And one assuming more here, I forgot to say that this stem in the middle is very light. So it don't have, so moment of inertia of this part is so small, so we don't have to account it. So the moment of inertia of the total yo-yo must be the mass of yo-yo times outer radius there. And this times angular acceleration. And one more thing for you here, and it's almost done here, the connection between these two. The connection between these two must be like this. Or, am I right? there comes a little problem for us. Or is it only problem for me? Which one are you using? Is the acceleration of the yo-yo what is there same than the outer radius of yo-yo, or the radius of the stem? Any opinions there? Which one we use? Because they are different. And I can give you a little hint there. The acceleration, how this string comes out there, must be the acceleration of yo-yo. And acceleration, how the string comes out there, depend of this inner radius. So I take this away and say the connection is there. Because really the acceleration when what the string comes out there must be the acceleration of the yo-yo. So it must be this connection now. This acceleration must be this smaller radius times angular acceleration. Angular acceleration is the same on the other side of yo-yo, but this shows us, because it's easy to think the speed the yo-yo comes down, it must be the speed that the string comes out from the yo-yo. So it must be the second one here. So now we can continue this one. So GR must be half time mass times. This is outer radius, of course, but now this alpha must be inner radius, like this. And now you have two formulas there. You have this one and you have this one. And now the idea again, I ask you to acceleration. And on these two formulas we have unknowns, or we have many unknowns there. But if we think that some of these we can measuring also, so I think the easiest way now to find out is we don't ask what is the tension of the wire. So if we take tension of the wire from this formula here, let's take it here. So the tension of the wire is half time mass times there's r power 2 divided by little r. It's little r power 2, so it's r power 2 per r power 2 times, do I get it right here? G is like this. Half time mass times radius power 2 divided by radius, and one more divided by radius times acceleration. And now if we put it on this formula here, what we get, this formula, what we get, mg minus half time m and this must be mass times acceleration. And as you see there, we don't need to go to the scale. We don't need to know the mass of this yo-yo. Oh, we can take the mass away there. And so we have here for the A, for the acceleration. So to accelerate, let's put this same side. We have acceleration one time. Then we take this part here plus half time and this must be G. So for the final answer, what we have for the acceleration of the yo-yo, I take it here, it must be we get answer like this. And every time we get that kind of result, we can little think, could it be correctly? And at least it must be smaller than acceleration due to gravity. It must be smaller than g. We know that it can't be the same. It must be smaller. And one check in there could be we can always do here. This value is always smaller than this acceleration is always smaller than g. So I think we have a right answer there. So we have about 15 minutes time, and I think we have enough time to do some car problems, moving car. And we are now the rolling cases, so we can take some dynamics problem of the moving cars. Now when we are going to rolling. But first I want to check one thing. I give you now car at the rest, and let's try to. This is a front wheel, this is a rear wheel, and I try to figure out the car here like this. Front, rear, there. And this is at the rest, this car now. So it's on the some surface here. And if I think the forces now, what we have there, we have normal forces here, normal force. I put it this A and normal force B there. We have a mass there, so we have a gravity somewhere. And now I show you, let's say that the center of mass is at this point. And we have mg here. And when we put this car moving, I think we need to find out, it's very important to us to find out these normal forces and how we can find out how these normal forces has divided. Because we know, of course, it's at the rest. This must be true. So this knowledge we have, NA plus NB is mg. And now this, notice this meaning, this NA is both the front wheels. So for the one wheel, if we calculate this way, is NA divided by 2. But I'll simplify this, or you can take it as a motorcycle, so we have only 2 wheels. But in the car case, if you're finding out the normal force A here, if you want to need the normal force A for the one front wheel, so you of course divide it by 2. But this is not my problem now. My problem is how they are divided. I know the sum of them is mg, but how I can find out the values of NA and NB? Any idea or knowledge of this? How I find this? Okay, I'll show you. For example, like this. To talk about this point must be 0 also. If we think this center of mass is an axis, so this normal force A gives a rotation, gives a torque on the clockwise, and this NB gives a torque of the counterclockwise. But we know this is not happening there. It's not rotating anyhow, so this must be 0. So we need to know one thing there. We need to know first of all, we need to know the place of the center of mass every time in this kind of case. And 2 dimensions. Dimensions of this one, I mark it dA, and this dimension, I mark it dB. Now we can easily find out here. So we have a force times moment arm. So NA dA must be NB dB. Now we have 2 formulas. We have 2 formulas, 2 unknowns. So normal forces can be solved if we know 2 things. We know the place of the center of mass, or the place of the center of mass is enough. If we know the place of the center of the mass, so we can easily find out what is the this distance from the center of mass to this line and center of mass to this line. Okay, I start with the rest, but now let's move this car. Let's put a moving car. Let's make a moving car. I try to make a same kind of car now here. Or I draw 3 cars. Three kind of similar cars here. Because only when I was a little boy, I like to draw cars, and still it's very funny to draw some kind of cars. So and I have now here 3 moving cars, and now it's depending. And if this first car is front driving, and this second car is rear driving, and this last car is 4D driving, forward driving, so both front and rear. So front driving, we give a torque to the front wheels, only torque to the front wheels. And now let's go back to this at the beginning of the lesson, this direction of the friction force. And now you think this car is moving this way. And this forces, of course, we have this normal force A here. We have normal force B here. We have mg here. And now if it's think, for example, it's moving as it accelerates this car, so net force is mass times acceleration there. This is a front driving car. And wait a minute. All the forces I have drawn there, they don't move that car at all. We need some force. If we're going to use Newton's second law, we need some force which is moving this car. And where that force is, we know this motor rotating this axis. It makes this front wheel rotation. It makes a rotation, but where is the force? Because we understand if it goes, its acceleration is this direction. So we must have some force that's moving this car on this direction. And surprise, surprise, same thing. And this problem I tried to show you at the beginning of the lesson. So this is this wheel. This is a road there. And now it's going from right to left. It's going this way. But if this road is very slippery, or anyhow, this wheel starts slipping like this. So to avoid the slipping, what's prevent the slipping is the friction force. It's a static friction force. And for the Newton's second, this is the only force which has a line, which has a direction to direction to motion. So this, there is our force. And again, it's a friction force. It's a friction force that prevents this car front wheel sliding. This is the only force what we have going from the right to the left. Of course, we have some resistance of air or something here, but this is the only force which goes. And if this is a front driving car, the back wheels go and they live in their own life. They're rotating freely. And in next case, I have a rear driving car there. So same way, but now the motor giving torque only to the back axis, the rear axis. So now we have the same. We have friction force here now. And same forces. We have a normal forces there, normal force A, normal force B here, and we have mg here. And our last case, what we have is a four-wheel driving, so then we must have a two friction forces there, and still we have this normal force A here, normal force B here, and mg here. And now if we go back to this, when we have this car at the rest case, and we are figuring out how we can find these normal forces, normal force A and normal force B, and we use this exactly the same way when we have a moving car. Because in this kind of situation, as you see, if we try to find out, for example, we tried out the biggest acceleration what we can give to this car without it's not sliding there. So we need to get here the maximum friction force, maximum static friction force. And for the maximum static friction force, we need the normal force. So we need this normal force A. And how we get the normal force A in this case. And now remember, I can take now way there because it's not, it's acting through the center of mass. We must use this formula again to find out the normal force A and normal force B. But now we have one more force here. And so if you, for example, this front driving car trying to use this is still true. If we put on this point, if we talk about this point here, it must be still in the 0. But now we have one more force here. So now in this case, let's do this. This force and this force rotating, if you need to axis is here, they both give a torque which is trying to rotate it this clockwise. So it must be NA times this dA plus this F mu S times, and now we need to also, from the ground, we need this distance also. We need also this distance. And mark it, for example, H. So it must be F mu times H. And the total, and this normal force here, and B must be, this is a minus sign because 0, I put it the other side of the equation, and I give you dB. So notice every time when the car is moving, doesn't matter if there acceleration, no, but the point, the values of this normal force is changed. They are not anymore same. When the car, sorry, you can see it from the beginning here. When the car is at this position, where it's at rest, this was very easy, and this is also very easy, but you must remember we have one more force here. So using this formula here, we have one more force here. Okay, but I think it's rather late already, and as I say, I don't give you any homeworks for the Easter, but next time we continue with this problem, this kind of problems. So what else I can say to you, that happy Easter for you, and let's see or hear about us at the next week. So bye-bye.
I have one question.
Yes, please, but
about the acceleration of the yo-yo.
Yes.
Because I found a video on YouTube about the problem of a yo-yo pull along the ground, and it calculates the acceleration by the big R, the big radius. So I am confused. If the yo-yo pull on the ground is calculated different acceleration with this kind of direction?
I tried to tell you that we are going to find out the acceleration of the yo-yo, and if we think the change of the velocities here, the yo-yo has the velocity is increasing all the time when it's going down. Yes, and the velocity of this string when it comes out must be same. It doesn't matter what is the outer radius there, because these velocities go same way. The velocity that yo-yo goes down must be the velocity that string comes out from the yo-yo. And if this is true, and I think it's true, the string comes out with some velocity, the tangential velocity of the string must be same than the velocity that yo-yo goes down. So if these velocities are same, so also the acceleration must be same. The acceleration of the yo-yo must be the acceleration how the string comes out. And acceleration how the string comes out is the tangential acceleration of this smaller part here. Do you get your answer? So this, which I ask you, this must be true, because the acceleration of the yo-yo must be same as the acceleration of the string. An acceleration of the string must be same as the tangential acceleration of this small stem there. So that's why we use the smaller radius, not the bigger radius.
Can I share my screen about that video? So
Let's talk a bit this about after Easter, because I need to go some meeting at which
okay.
starting at 10 o'clock. So, but if you want to send me something, if you don't buy my answer, so send me, for example, email. I can answer for your email. Okay. So bye for all of you, and see you after Easter.
Bye.